Thank you. And reasons to believe the organization I founded, we have all kinds of social media outlets. We have a 24/7 YouTube channel, so feel free to subscribe. It's all free. And at the book table out there, let me see if I can get this to work. Here we go. Yes. We're giving away a copy of my book, Always Be Ready. So just scan that QR code or go to the table out at the back, and they'll give you a free copy of my book, Always Be Ready. But what I want to share with you today is about my latest book. I've now put out 22 books, and this is the 5th book that I have written on the fine-tuning argument. Let me see if I can move this again. Here we go. Maybe not. Let me try this. Oh boy, okay. Yeah, nothing's happening here. There we go, okay. And, okay, wrong direction, I have to go down, okay. There we go. All right, I think I got it. Yeah, I've produced 5 books now on the fine-tuning argument for God. Traditionally, that's been the go-to scientific argument for the existence of God. It goes all the way back to the early church fathers. But what I want to share with you is how we can develop an exponentially stronger fine-tuning argument for God. And it's based on the biblical principle that God began his works of redemption before he created anything at all. And yes, I think we're working well there. That it tells us in 2 Timothy 1:9 that the grace that was given us in Christ Jesus before the beginning of time, and in Titus 1:2, the hope of eternal life, which God, who does not lie, promised before the beginning of time. This is just 2 of 7 texts in the Bible that tells us, number 1, that time has a beginning. And I spoke yesterday at a conference basically laying out the evidence that we now have that time indeed was created. The space-time theorems prove that there's a beginning to space and time. And of all the holy books that undergird the religions of the world, the Bible stands alone in saying, not only does the universe have a beginning, time is a beginning, space is a beginning. But what the Bible tells us is that God began his works of redemption before he created anything at all. The grace that we receive, the hope that we get, was actually put into effect before the beginning of time. In other words, before the triune God created anything at all, they worked out their plan of how they were going to bring billions of human beings into a redemptive relationship where they would be delivered from their sin and evil and enter into an eternal relationship, loving relationship with the Creator himself. What this implies scientifically, if indeed God began his works of redemption before he created anything, it implies that everything that God creates is for the purpose of redemption. Now, what I've seen amongst my peers in astronomy and physics, they will observe the universe and its characteristics, and they discover that many of those characteristics must be fine-tuned to make life possible. And the fine-tuning is even more spectacular if you want the equivalent of human beings to exist in the universe. But I don't know of any work until this design to the core book that actually puts it in a redemptive context. What does the fine-tuning need to be like for billions of human beings to redeem from their sin and evil? So what I've done in the book Designed to the Core is say, well, let's look at the universe at all different size scales, from the universe as a whole, all the way down to the objects that are right close up to us, the comets, the asteroids, the moon, the earth, the sun, the interior structures of all these objects, test to see whether or not is this really designed with redemption in mind. And that's exactly what I've been able to demonstrate. Spent 3 years going through the scientific literature, and indeed we see that the fine-tuning argument for God increases exponentially when we put it in the context of what's needed to make possible the redemption of billions of humans from their sin and evil in a short period of time. Now, the opening chapter, I talk about the universe, how we need a just right universe. And this is something that's been written about in many books. I've got over 50 books in my library, written mainly by people who are not believers, how when we look at the universe, we see overwhelming evidence that has been highly fine-tuned to make possible the existence of life and human beings in particular. But what I've added is how much the universe has to be designed in order to make the redemption of human beings possible. In particular, we discover that each of the laws of physics, gravity, electromagnetism, the strong and weak nuclear force, the size of the universe, the age of the universe, the mass of the universe, all that must be exquisitely fine-tuned in order to make redemption possible. The laws of physics themselves are chosen by God as a tool to bring about the redemption of humanity. We need gravity. We need thermodynamics. Jesus himself said, "In this world you'll have tribulation, but take heart, I've overcome the world." Tribulation, that's an inevitable consequence of gravity, electromagnetism, thermodynamics, and the strong and weak nuclear force. We'll have that in this universe. But what we see in the Bible is it's a two-creation model. God will use this universe as a tool to eradicate evil and suffering once and for all. And then he'll take us into a new creation. But we see in Revelation 21 and 22, in the new creation, there is no death. There is no decay. We have a building in the new creation that defies the law of gravity. There will be no gravity. There will be no electromagnetic radiation. There will be light. Everything will glow with light, but there'll be no darkness. There'll be no shadows. We're going to be introduced to radically different laws of physics because we no longer need the laws of physics we see or the universe in which we live because evil and suffering will no longer exist. But what you'll also see is we have to be in a just right super galaxy cluster. And only in the last few years have we astronomers even been able to define what a super galaxy cluster is. It's a cluster of clusters of galaxies. But only recently we've been able to discern the structure and the boundaries of these super galaxy clusters. I'll show you a few images in a minute. And we have to be living in a just right galaxy, and a just right galaxy cluster, and a just right galaxy group. And we need to be living in a just right galaxy. Life is only possible in a spiral galaxy. Other galaxies, the stars are jammed way too tightly together in order for stable orbits of planets to go about stars and for those planets to be protected from radiation. Now, we astronomers have been looking throughout the entire universe trying to find a galaxy sufficiently like our Milky Way galaxy that it could be a candidate for advanced life. Those of you who are Star Wars fans, I want to disappoint you. There is no galaxy far, far away. We've looked far, far away. We don't see any. But what I've done in the book is to show you the 18 galaxies that come the closest to matching our Milky Way galaxy in its capacity to support life. I'll show you 11 of them this morning. And so what we see here, let me move it up. Here we go, maybe. Here we go. The upper left one you might recognize. That's what's called our sister galaxy. It's the Andromeda galaxy. However, when you look carefully at that image, you notice that the spiral arms are distorted. The outer spiral arms are as big as the inner spiral arms, and it also has a very active and has a very large supermassive black hole in its core. And these other spiral galaxies, you'll notice that the spiral arms are distorted, and there's lots of spurs and feathers between the spiral arms. Here are some galaxies that come even closer. In fact, the one that you see in the center upper, that's the galaxy that comes the closest to matching our Milky Way galaxy. But it has a supermassive black hole in its core that is actively pulling in matter, and it basically is radiating the entire galaxy with dangerous radiation. And also you can see that the spiral arms are distorted. The Milky Way galaxy is in the bottom right. You can see how symmetrical the spiral arms are, how few feathers and spurs exist between the spiral arms, and unlike these other spiral galaxies, It's got a quiet nucleus. It's not pouring out deadly radiation. And we not only need a just right galaxy, we need a just right star. And so let me move this along. And what we're noticing as we go from the super galaxy cluster to our galaxy cluster, our galaxy group, our galaxy, our star, our planet, our moon, in each case, as we survey the entirety of the universe, we're not finding anything that's anywhere like it. Each case, our star is unique. It's unique in the sense that for 70 years, astronomers have been scouring our Milky Way galaxy, looking at tens of millions of stars, doing the same thing in the Andromeda galaxy and the large and small Magellanic Clouds, searching intently to find a star that's sufficiently like the sun that it could be a candidate to have a planet orbiting it in which advanced life is possible. We have found many stars that are twins of one another, but we've yet to find a star that's a twin of the sun. It's the only star we found that's a candidate to have advanced life orbiting it. And it was back in 1995 that astronomers discovered planets orbiting other stars. And they were excited and saying, we're going to find hundreds of planets that are just like the planets in our solar system. Well, here we are in 2022. The number of discovered and measured planets now stands above 5,000. And of those 5,000, not a single one looks anything like any of the planets in our solar system. Not only have we not been able to find a twin of planet Earth, we've not been able to find a twin of Mercury, of Venus, of Mars, of Jupiter, Saturn, or Uranus and Neptune. And this led to a discovery that each of the planets in our solar system must be exquisitely fine-tuned to make advanced life possible on planet Earth. Mercury must be exactly the way it is. Venus must be exactly the way it is. Mars and all the rest of the planets must be precisely the characteristics that they possess in order for advanced life to be possible here on planet Earth. So come Thanksgiving next month, I want you not only to thank God for our amazing planet Earth, but please thank God also for Mercury and Venus and Mars, Uranus, Neptune, because without those planets being precisely the way they are, there'd be no possibility for you to have Thanksgiving dinner on your table. And it's not just that the 8 planets in our solar system all must be exquisitely fine-tuned. This is even true of the asteroid and comet belts that we see in our solar system. We have 5 of these asteroid and comet belts, and now we've got the technology to discover asteroid and comet belts around other stars. And what we discover is 80% of the stars we look at do not have any asteroids or comets at all. And we now know why. They're gas giant planets migrate so far inward towards the host star, they basically eradicate or erase or scatter out all the asteroids and comets. And then the other 20%, their gas giant planets don't migrate at all. And consequently, they have asteroid and comet belts 1,000 times bigger than we see in our solar system. And if you got 1,000 times as many asteroids and comets, that means we're going to get regular bombardments of our planet by these comets and asteroids. And that would make civilization rather unpleasant to have these things crashing into the Earth all the time. One wiped out the dinosaurs 66 million years ago. So you don't want that happening every day. On the other hand, you don't want any delivery at all, because our planet has a mass where the gravity is strong enough to retain carbon dioxide, strong enough to retain oxygen, but it's barely strong enough to retain water. And so we actually lose a tiny amount of water to interplanetary space every day. But that tiny amount of water that we lose is replaced by the water we gain from comets. About 10,000 tiny comets bombard our Earth every day, and comets are 85% frozen water, so we get a delivery of water that replaces the water that we lose. And moreover, we get the occasional asteroid crashing into the Earth, And many of these asteroids are super endowed with heavy elements. So for example, 80% of the gold and platinum that's in circulation today comes from an asteroid that crashed just outside of Johannesburg, South Africa. 50% of the nickel in circulation today comes from an asteroid that crashed on the north shore of Lake Huron near Sudbury, Ontario. So we are blessed by having just the right delivery of asteroids and comets to planet Earth. And of course, we need a just right Earth. Over 400 characteristics of the Earth must be fine-tuned to make advanced life possible. And we have a just right Moon. And now we know that 23 distinct characteristics of the Moon must be fine-tuned. So one example is our planet Earth has a stable rotation axis tilt. It moves between 22 and about 24.5 degrees back and forth over a 41,000 year period. That's possible because we have a small planet being orbited by a gigantic moon. That's what stabilizes the rotation axis tilt. All the rest of the planets in our solar system, the rotation axis does this, flips back and forth. And so we have the stable rotation axis. That's just one of the features we gain from the moon. Now, I mentioned earlier that we've just gained the technology to define super galaxy clusters, and I want to show you a slide of the map of the super galaxy cluster in which we live. Let me see if I can advance this. Here we go. There you go. That's the Laniakea super galaxy cluster. It's a cluster of clusters of galaxies. But what's unique about our Laniakea super galaxy cluster is the galaxy clusters and galaxy groups are strung out along these long filaments. And so that little red dot there basically shows where our local group of galaxies exists. It's at the nexus of 3 subfilaments. If you're not near a filament or a subfilament, there won't be enough tiny dwarf galaxies there to sustain the spiral structure. But notice that we're in a grouping of galaxies that's in the least dense part of the Laniakea super galaxy cluster. And we're living in the smallest galaxy group of all the galaxy groups that exist. And notice that the big clusters of galaxies are all tilted way over to the right. The Virgo cluster, the Centaurus cluster, the Hydra cluster, those are clusters where you got so many galaxies jammed so tightly together that many of those galaxies have really huge supermassive black holes that basically radiate not the entire galaxy with deadly radiation, but even all the galaxies in its vicinity. Fortunately, we're 53 million light years away from the nearest one of those nasty supermassive black holes, far enough away that it doesn't disturb our civilization. Now, we astronomers have found tens of thousands of these super galaxy clusters in the universe, but this is the only one where we see the galaxies and galaxy groups strung out along these long filaments. It's the only one where the galaxy groups are relatively small, and even the galaxy clusters are not that big. Let me show you a typical super galaxy cluster. This is the Shapley super galaxy cluster. And here you see, you've got these big clusters of galaxies jammed so tightly together that you really don't have any voids. You really can't see any filaments there. And it's filled, because of the density of galaxies, it's filled with these supermassive black holes that radiate deadly radiation. And the galaxies are so close together, they're gravitationally disturbing one another. And this is typical of super galaxy clusters. So for example, we see the Perseus-Pisces super galaxy cluster, the Leo super galaxy cluster. The one that comes the closest to matching our Laniakea super galaxy cluster is the one in Ursa Major. And what we see here is that yes, we do have galaxy clusters strung out along an arcing filament, but notice how big these the clusters of galaxies are and how close together they are. And this is a place, again, where galaxies are jammed too tightly together, and there's just too many supergiant black holes radiating deadly radiation. And so ours sticks out like a sore thumb. It's the only one where we see the galaxies and galaxy groups strung out in such a way that there is no gravitational disturbance of any significance for the galaxies in the local group. And we've done it, reasons to believe, is actually create a map of the local group of galaxies. And what we've discovered, yes, there we go, is that we live in a galaxy group that's like none other in the universe. And in our universe, there are literally millions, billions of galaxy groups. But ours is the only one that doesn't contain a single giant galaxy. Ours is the only one that contains only 2 large galaxies. Most of them contain dozens of large galaxies. Ours has only 2, the Andromeda Galaxy and the Milky Way Galaxy. It's also the only grouping of galaxies where the large galaxies are far apart. What we see in other galaxy groups is the large galaxies are about this far apart. What we see in our local group is that they're very far apart. This is all done to scale. And also we see it as only a few large dwarf galaxies, only 5. And then it has several hundred tiny dwarf galaxies that don't show up in this particular image because of how faint they are. But because the Andromeda Galaxy is 2.5 million light years away, its gravity doesn't disturb the spiral structure of our Milky Way galaxy. And because of the fact that the 3rd biggest galaxy in the group, which is the Large Magellanic Cloud, which you see just below the Milky Way galaxy, it's got just the right mass, just the right diameter, and just the right distance from our Milky Way galaxy that it actually acts as a funnel, pulling in these tiny dwarf galaxies into the core of our Milky Way galaxy in such a way as to sustain the spiral structure. If spiral galaxies are not consuming on a regular basis tiny dwarf galaxies, the spiral structure collapses, and now the stars are too close together. So we refer to the large and small Magellanic Clouds as the dietitians for our Milky Way galaxy. They ensure that our Milky Way galaxy gets exactly the right diet to sustain the amazing spiral structure and to keep that structure stable. Now, just a few months ago, the Event Horizon Telescope team, people think that the James Webb Space Telescope is the most powerful telescope that we have. Actually, that's not the case. What radio astronomers have done is they've linked together about 20 radio telescopes around the world, and they're able to link them together in such a way as to create a telescope with the equivalent power of a 6,000-mile diameter telescope. And that's the only telescope in the world that's got the resolving power to actually detect and measure the event horizons of black holes. What is an event horizon? That's the distance from a black hole where nothing can escape. However, just outside the event horizon, any matter coming in towards the black hole gets converted into energy with 10 to 42% efficiency, which explains why we would expect that there would be a bright donut of light around the black hole. And we've only been able to image that for our Milky Way galaxy, and it took 4 years of dedicated observations to come up with this map. But notice, you do see the event horizon, but this is really quite a fuzzy image. And the problem is it's very faint. I need to move it along. Yes, thank you. There we go. That just got published a few months ago. It took 4 years of dedicated observations to develop this image. They're hoping to come up with a better image, but it'll probably take another 10 years. But the reason why this was so difficult to detect is that for the last couple of million years, our Milky Way galaxy's supermassive black hole has been on a starvation diet. Most supermassive black holes are pulling in objects as big as moons and planets and stars and giant molecular clouds. Our Milky Way galaxy for the past 2 million years has been on a diet of tiny comets and tiny asteroids. And therefore, we don't see a lot of light around the event horizon of the black hole. But we do know that our black hole wasn't always that quiet, mainly because we see this image here, which shows two gigantic X-ray bubbles. And these bubbles are expanding. And as we measure the expansion rate, it tells us about 2 million years ago, our supermassive black hole was pulling in an object about the size of a planet, and it generated deadly radiation. But that was 2 million years ago. For the last 2 million years, it's been on a starvation diet. And particularly the last 100,000 years, it's been on an exceptionally weak diet of matter being pulled in, basically just gas clouds, tiny gas clouds coming in. Consequently, during the past 100,000 years, our supermassive black hole has been so quiet that we've been able to develop global civilization and build up a population of billions. And just a few months ago, astronomers discovered that similarly, the supermassive black hole that's in the Andromeda galaxy, it's 35 times bigger than the supermassive black hole in our Milky Way galaxy. And ordinarily, even though it's 2.5 million light years away, that would be a problem for advanced life on planet Earth. But astronomers have discovered, just like our Milky Way galaxy has been on a starvation diet for the past couple of million years, likewise the Andromeda galaxy, at least for the past 100,000 years, has likewise been on a starvation diet. And therefore, advanced life is possible on Earth. And you say, well, if there is a creator, why would he create black holes? Well, it turns out if you don't have black holes in the universe, you're going to be missing 25% of the elements in the periodic table, including two elements that are crucial for we humans to exist. And these are elements that are only made when neutron stars merge together to make black holes. And when that happens, you generate about a quarter of the elements that are, well, half the elements that are heavier than iron. So that's where our uranium comes from, our thorium, our gold, our platinum. That's where our iodine comes from. And so if it wasn't for these black holes, there'd be no possibility for life. And one of the papers that I got published in a peer-reviewed journal was this one called Black Holes as Evidence of God's Care. Put that into any search engine, it will pop up, and you can read the whole paper for free. You can also read for free the reviews I got, because I drew 3 atheistic astrophysicists who reviewed my papers. One of them thought the paper was really good and said, I want this to get published. The other 2 were really disturbed about the God factor that I was mentioning and said, no, this paper needs to be rejected. But they gave me an opportunity to respond to the reviewers. And you can also see online my responses to the reviewers. And basically what happened is the paper got accepted for publication. And in that particular issue, my paper was first for a number of reads. In fact, it exceeds by a factor of 2. But let me finish this off with what I think is one of the most profound evidences we see for fine-tuning to make our redemption possible, and that has to do with our unique moon. I mean, we see moons all over the solar system. We're actually detecting moons outside of our solar system, but we're noticing these moons are always tiny relative to the mass of the planet. Our moon is more than 50 times bigger than any other known moon relative to the mass of its host planet. For example, our moon comes in at about 1.5% the mass of our planet, whereas what's typical is something like 0.01%. And that's because our moon formed like no other moon. Our solar system began with 5 rocky planets. There was Mercury, Venus, Earth, and Mars, and the planet Theia. Well, what happened early in the solar system's history, Theia and the Earth collided with one another, which caused the Earth to become more massive, but also create a debris cloud around the Earth that coalesced to form the moon. It explains why we have a relatively small planet orbited by a gigantic moon. But during the first 560 million years, of the existence of our solar system, what we notice is that our sun was pouring out intense particle radiation, gamma ray radiation, X-ray radiation, and flaring activity that's 100,000 times greater than what is happening today. That takes you up to that little green dotted line. And the radiation coming out from the sun was so intense that it would have sputtered away all of Earth's water and all of Earth's atmosphere. What prevented that from happening was that the Earth at that time had a very strong magnetosphere, much stronger than we have today. However, as scientists studied this, they realized there's no way the Earth could have had that strong enough of a magnetosphere by itself. And they realized the answer was the moon. Now, this is how far apart the Earth and the moon are right now. But this is how far apart the Earth and the moon were 4 billion years ago. And because we need to advance the slides, thank you for reminding me of that. That's the Earth and the moon right now, and this is where they were 4 billion years ago. And because the moon and the Earth came about as a result of this collision, Earth began with a very hot core, and the moon began with a very hot core. Both of them had a hot liquid iron core. And because of how close together the Earth and moon were, the tidal interaction between the Earth and the moon was sufficient to circulate the liquid iron in both the core of the moon and the core of the Earth. So both bodies had a magnetosphere, a strong magnetic field that generated a magnetosphere. And because of how close together they were, the magnetosphere coupled. And it was that coupled magnetosphere that prevented the particle radiation from the sun sputtering away all of our water and all of our atmosphere. And the authors of the research paper concluded their paper by saying, this is a habitability requirement. It is the most profound habitability requirement. The only way you can have life on a planet is if you have two planets colliding with one another, just like Theia and the Earth collided, where you get the formation of the moon, where both have a hot interior core, and the moon begins to spiral away from that planet, just like the moon spirals away from the Earth. If it doesn't have all those features, there's no way that you're going to retain water and atmosphere on the planet. And years ago, when people were working on the planet formation model, they said, we got way too much design here. We need to redo the models in order to eliminate all this amazing design we're seeing here. They redid the models and they came up with even more design. This is all published in the British journal Nature, and Tim Elliott wrote an article saying, all this extra fine-tuning is causing us philosophical disquiet. Well, now that this philosophical disquiet has raised exponentially, and explains too why we see the history of life that we do on planet Earth, where for the first 560 million years there is no life. The solar radiation would have made that impossible. Microbes are much more tolerant to solar radiation, and explains why for the first 3 billion years of life history, all we have is microbes. The sun has to quiet down enough to make possible plants and animals, and then there's only a 100,000 year wide window where the sun's radiation is quiet enough where we human beings can exist. And then we astronomers have been scouring our galaxy trying to find a star that's luminosity stability is like the sun. Well, the top figure here basically shows you the luminosity stability of the sun. What you see at the bottom is a star out of the millions and tens of millions we've looked at that places second. Our star, the sun, is 5 times more stable in its luminosity stability than the second best star we've been able to find. And if that weren't the case, none of you would be able to sit here together this morning. Again, as you walk out, do pick up our book, Always Be Ready. It's free. And remember nothing else from my talk today. I know I was a little technical here. Just remember this, a principle in Job and Psalms. The more we learn about nature, the more evidence we gain for the supernatural handiwork of God that makes possible the redemption of billions of human beings from their sin and evil. Thank you.